Hi guys, here's example 2 of our quadratic models. This is for exercise 3L. This one again taken from the book, but it gives us a few things to talk about. So as you can see with this one, they've given us a situation and even a little graph, but we're going to draw our own graph to get a bit more detail. Cricket ball is thrown by a fielder. It leaves his hands at a height of 2 meters above the ground. This gives you some indication of what this y-intercept here will be. It's leaving his hands from 2 meters above the ground, the distance of 0 from him, so that's right there at the y-intercept. The wicketkeeper takes the ball 60 meters away, so we have this horizontal distance of 60 meters to the wicketkeeper, and he also takes it at 2 meters above the ground. That's nice, it gives you a symmetry. It's 2 meters above the ground at either end. It's known that after the ball has gone 25 meters, it's 15 meters above the ground, and that's that point there. And that's not at the turning point, because 0 to 60, symmetry, halfway, 30, the turning point's going to be at 30. Path of the ball is a parabola, upside down parabola. It's got equation ax squared plus bx plus c. Find the values of a, b and c. Sounds like a simultaneous equation sort of problem. Unless those points that you're given fit into a different format. So let's just start with that. If we were doing quadratic models, we might have that format, the one given us, or we might have this format if we were given the turning point, HK. Turning point up there, HK, but we don't have that. Can't use that model. Or we could even use this model if we were given the two x-intercepts, but we're not, because the points we're given are 2 meters above the ground. So we can't use the turning point form, we can't use the x-intercept form, so we need to use the general form, this one here. Also, there are 3 coefficients in the general form, a, b and c, so we need 3 pieces of information. And if we look at our graph, we might have those. I'm going to redraw the graph here on the right. I'm going to draw it slightly different. We've got y up here, which is also height, and we've got x over here, which is also distance, and we've got a point there which I'm going to label as 0, 2, and I've got another point there which I'm going to label as 62, and we've got a parabola. I'll just try and get that roughly symmetrical. It's not very well good, but doesn't matter. And there's a point just there at 25, 15, and I'm pretty confident with the symmetry that that's going to be 30. To find the maximum height, y max would be that value y there, which would be there. The maximum height's there, but we would need to get the equation, sub in x equals 30. Find the height of the ball when it is 5 meters horizontally before it hits the wicketkeeper's gloves, which would be just there somewhere, 5 meters away from the wicketkeeper's gloves. What's that point? That's what that last question's asking us. So, what are the 3 pieces of information that we've got? We've got 3 intercepts, or 3 points, sorry, 3 coordinates. We've got the 0, 2 coordinate, we've got the 25, 15 coordinate, we've got the 62 coordinate, and they can all be subbed into this formula. And so if we sub in 0, 2, we would get y equals 2. Equation 1. That was too easy. If we subbed in 25 and 15, we would get 15 y equals 2, which is also c equals 2. It tells you that c equals 2. The second point, 15 equals a times 25 squared plus b times 25 plus 2, because we now know what the c is. Just got to rearrange that slightly, take the 2 over to this side, 13 equals, and probably expand out these values. So 25 squared becomes 625a, I think, and 25b. That's equation 2. To get equation 3, we sub in the, there's equation 1, there's this down here. We sub in the 2 for the y, and we get a times 60 squared and b times 60 is the x, plus 2 there. If I take that 2 over, I'm going to have naught equals, and 60 squared, I think it's 3,600, isn't it? 3,600a and 60b. And we've taken that with minus 2 from both sides. There's equation 3. Now we would need to take equation 2 and 3. So the 13 equals 625a plus 25b, and the naught equals 3,600a plus 60b. Those are the two equations we're working with, and we need to solve them simultaneously. Equation 3 could be divided through by 60. That would work. Another way, of course, at this stage is to do K's system of simultaneous equations. And I have put the example of how to do that, and you did it earlier in chapter 3, on the OneNote. On the social stream, you can see the hints about how to go about doing system of simultaneous equations. Might be a good point to stop the video and use your CAS and use the 3 points that you've got here. There they are there, and you need to put them into system of simultaneous equations to find the a, b and c. So you can go ahead and do that. If you're going to do it the long way, you divide equation 3 by 60, you'd get naught equals naught equals 60a plus b, of course. Yeah, 60 is 3,600. So 60a plus b. Call that the new equation 4. Probably going to do a b equals 60a, negative 60a, and then a sub into equation 2 like that. That would be one way of solving it. I think if you look on my OneNote now, you can see the working for the rest of this question. So if you go to the OneNote for quadratic models, you'll see the working for the rest of this question. You can also look in the textbook how this can be solved simultaneously and how the other questions can be answered. So I don't think I'll go through it any longer here because there's quite a bit to do, but if you look at the example in the OneNote, you can see that. So let's pause that there.